Good day guys, how's it going? This is the Math Base, and today's challenge is if we're given the information sine theta equals 0.7, how do we find the sine of pi minus theta, pi plus theta, 2 pi minus theta, or just negative theta, without a calculator and without knowing the angle of theta? We don't have much to work with here, which is why we need symmetry equations. There are 12 equations to learn, and there are a few ways to remember them, which I will go over in this video, including a super easy table format you can use as a reference. So, let's get to work. Let's first understand how this works. Presume theta is an acute angle, so it's in the first quadrant. Symmetry dictates that if I were to reflect this angle position to the second quadrant, I would get a symmetrical angle such that it is pi minus theta. For example, if theta was 30 degrees, its symmetrical angle in the second quadrant would be 150 degrees. Or in radians, pi on 6 would be symmetrical to 5 pi on 6. On the other hand, if we are reflecting all the way into the third quadrant, then the angle is pi plus theta. And similar to this, the fourth quadrant is 2 pi minus theta. If you watched my video on solving trig equations, you'll notice we use the same concept there to calculate answers from a reference angle, because it's all about symmetry. Now, a special case we need to address is negative theta. When we subtract theta from 0, the angle is found in the fourth quadrant and is symmetrical to theta. Since 0 and 2 pi are the same angle, we can say 0 minus theta, or just negative theta, is the same thing as 2 pi minus theta. Don't treat it any differently. So to summarize, when we have an acute angle of theta in the first quadrant, we can generate symmetrical angles to it in the other three quadrants using these formulas. This also works for obtuse and reflex angles, which we will see later in the video, so keep watching. Combine this with our knowledge of the cast system, and we can build a tabulated version, which I find much simpler to work with compared to memorizing formulas for sine, cos, and tangent. Here's how we build it. Setting up a 3x4 table, the first column displays your formulas respective to their quadrants, and the last three columns relate to sine, cos, and tangent of theta. The whole point of this topic is to rewrite these crazy formulas into its simplest form, like sine theta, cos theta, or tangent theta, depending on your trigonometric term. So by casting, sine is positive in the second quadrant, meaning sine of pi minus theta equals positive sine theta. In quadrant 3 and 4, sine is negative, so these other formulas equate to negative sine theta. You can do something similar for cos and tangent, based on where they are negative or positive. Let's use this table or the symmetry equations to solve our question from the start of this video. Given sine theta is 0.7, and all we know is that theta is an acute angle, we can evaluate these four expressions without knowing theta by using symmetry equations or the table. In both cases, we can see that sine pi minus theta should be positive, so it's just 0.7. Sine of pi plus theta sits in quadrant 3, where sine is negative, so it's negative 0.7. Similarly, for the last two expressions, which are essentially the same thing, they are both in the fourth quadrant, so they're also negative 0.7. Whether you want to use the equations directly or use the table to navigate, either tool works great for when theta is acute. But this gets confusing when you deal with obtuse or reflex angles, and the table will become a lot more useful here with a minor improvement. Allow me to explain. Let's say we are given cos of x as negative 0.8, and x is an obtuse angle. Surprisingly, our symmetry equations will still work, and you just need to use x instead of theta. Following the equation rules, cos pi minus x should be negative of cos x, right? So using some basic arithmetic and algebra, we can see how the negative of negative 0.8 turns into positive 0.8. Applying the same principles to the others will yield similar results, but I don't enjoy doing it this way because there's too much maths involved when it should be straightforward. This is where the table stands out. Instead of thinking of positives and negatives in our table, let's think about it in terms of what needs to change their signage and what does not. So for example, cos of pi minus theta would need a sign change, but cos of 2 pi minus theta does not. Since cos x is negative 0.8, cos pi minus x changes the sign to positive 0.8. Cos pi plus x also needs a sign change, but cos 2 pi minus x and cos negative x does not change, so these two are identical to cos x, negative 0.8. Let's try this out for the last one, but with a slight twist to the question. Now we're given one of its symmetry equations as information, and we don't really know where alpha is. But don't think about maths anymore, just think about changing the sign or not. Looking at the table, we are not supposed to change anything for pi plus theta in relation to tangent. So tangent alpha should also be negative 2.7. Now that we have that, we can go ahead and find the rest. It looks like tangent pi minus alpha needs a sign change, so this becomes positive 2.7. Tangent 2 pi minus alpha, or tangent negative alpha, also needs a sign change, so they are both positive 2.7 as well. Done. You might face other questions which look similar, like using tangent alpha equals negative 2.7 to find cos alpha, but they have a completely different approach and use something called the Pythagorean identity. It goes through quite a bit of algebra and has a very interesting formula for cos and sine. So if you don't want to miss that video when it comes out, make sure you hit that bell and subscribe. And I hope this video has helped. If you guys have a specific question you would like me to work on, let me know in the comments below. Otherwise, thanks for watching, and I'll see you next time.